All right. Reflection, diffraction, and refraction. You can write that down. Got that? Yeah? Got that? Okay. So, lot to do. Lots. First one, reflection. So what do we mean when we say a wave reflects? What does that mean? You know this word from English, don't you? So, in physics, same idea. Reflection is the change in direction of a wave at a boundary between two different media so that the wave moves back into the medium it came from. And so the most common example, of course, is light against a mirror or sound and water against a wall. Now, I think it's just enough to write this down, but just to give you a very clear understanding here, what's happening is you have medium 1 and medium 2, and the wave moves in, hits this, and instead of continuing forward, it comes back. So the simplest example I can give you is if this is air, and this is a mirror, and this is light. That's the simplest example of reflection. But there are many examples. So for example, my sound will be reflected from the wall back into the air. Example. So it's just enough to write that much down. If you want, you can write down the example, but it's obvious. The light and the sound, and there's a picture of a man in front of a mirror, so we're all clear here. Can you see okay, Kim, from there? Are you sure? Okay. I can trust you? Okay. Everybody's sick. You're sick. You're sick. Are you guys sick? Okay. He's sick too. These guys are weak. I heard George is still out of the country. Yeah? Nobody's been talking to him on WhatsApp? No. He said he'll be back, I think, in a week.
Really?
That's what I heard. Whether that's going to happen, I don't know. You seem surprised by this.
He said he want to go to another country and to drop this course.
Yeah, I don't know what his plans are.
This in the.
Do you know where he wants to study?
Australia or something like that?
Yeah. There's a student in January who studied in Australia last year. He studied English there.
Yeah, because he said he can do something like foundation about his course. It's not like now we do the physics of.
He can
he
specialize.
Said,
yeah.
He said the course is not useful for him.
So he thinks he has a foundation program which is more suitable for him. What is it that he wanted to study? I forget.
I forgot as well.
What was it? Alright, so he must have found some foundation program in renewable energy. Okay.
Yeah, some if I study at DCU, I can do a psychology foundation.
Really?
Yeah. And it's very easy to do that because you're interested in the course.
Are you sure you don't do any maths? Because I know about the DCU foundation program. I think it has maths in it too.
A bit
of maths, yeah.
Yeah, no physics and chemistry.
No physics and chemistry, yeah. Okay, but lots of English. Yep, lots of English. Okay, the next one, diffraction. Does anybody know this word? Diffraction.
Is it dispersing?
Yeah. So diffraction is when the wave, it's also that one, it bends around obstacles or when it spreads out. So here's the picture. When the wave moves in a big gap, it really kind of stays the same. But when the wave passes through a small gap, it spreads out. It looks like it widens as it comes out. Okay? This is called diffraction. You can actually see this when you cross the bridge in the city centre. If you look down, you can look at the wave coming out from under the bridge, like O'Connell Street. You see it looks like it spreads out a little bit. So this is called diffraction of waves. I think you should draw the picture. If you're wondering what the small text is here, it's not very, very important. All it says here is wide gap, small diffraction, narrow gap, large diffraction. But I mean, you don't need to write that, it's the picture. Got that? What's so funny? You guys are always laughing. I'd love to know what the joke is. It must be wonderful. No? Alright. Continue. You got that, Cho?
Just one.
Okay. Okay, yeah. Oh, good grief. Okay. So tired today. Right. And the last one is refraction. And this is when the wave changes its speed because it changes its medium. So here's the most famous example. When you have light that passes through something like glass. So it looks like that the light bends. What actually happens is when the light moves from air to glass, it slows down. And this slowing down actually causes it to change its angle. And then when it moves from glass to air, it speeds back up, and this change in the speed causes it to change its angle. Okay? So this is this is the most important one because this is the one that we study a lot in physics, this refraction. So it's the change in the speed, and it's also good to know that this means it changes its angle as it passes through from one medium to another. Yeah, draw this one too, please, yeah. You didn't need to draw the man in front of the mirror. I think that's okay. I can read it, yeah, what do you... The word? Oh, is the change caused by the change in the wave speed? Is that what you need? Yeah. Do you need to move, Kim? You don't want to sit beside them and get sick. Is that it? Do you need to move? Or you don't want to sit beside them because you'll get sick?
We need to draw the picture.
Please, yeah. Is that you knocking it, Andek?
No.
No. It's not great. Yeah, it's not great. It's not great. It's very light, so it's so easy to move. Okay. Is today mosque day? Pizza day?
Today they have prayed some.
Yeah, so does that mean no food today? Pizza day. Is there a good bargain anywhere?
Not sure.
No. I like pizza, but I kind of feel like it's expensive sometimes.
It's €6 for a small one.
Where?
The pizza place.
The pinheads.
No, not exactly pinheads, but
Just across the road.
Ah, the traffic lights.
yeah,
Yeah. I like that place.
yeah, that's
Yeah,
nice.
it's good, yeah. €6?
Yeah.
Small pizza?
Yeah.
Any drink with it?
Regular pizza, like English.
Yeah, but you get any drink with it? Just the pizza?
Yeah. But if you get
Okay.
like a canned drink, it'll be €150.
It's okay. Not a bargain, but it's okay. Alright, did you get this? Yeah? Okay. Now, some materials allow the light to pass through it more freely than others. It's a little bit like, remember, we have resistance. Some materials allow the current to pass through easily. Same idea with light. Some materials will slow the light down. For example, light moves slower in glass than air. It also moves slower in water than air. It moves slower in these materials. So we need a way to measure this, and we measure it by what's called this. Now, don't write it down just yet. Refractive index, and it's a measure of how fast. And we actually use yellow light as the standard in the experiments. So what you do is you take yellow light and you shine it through a material like glass or water or whatever, and you calculate this thing called the refractive index, N. And the definition is it's the speed of light normally in a vacuum divided by the speed in the material. Now, the thing about this is, which will always be bigger? In fact, the C is always bigger than the V, because what happens is the light is always slowed down when it goes through a material. So if the C is always bigger than V, then what can you say about the value of N? It's always bigger than 1. And in fact, in only one special situation will the N equal 1. When's that?
C equal V.
When C equals V. And when does that happen? Or a vacuum, which is nearly the same thing. Okay? So in other words, the bigger the value of N, the slower the light is moving in the material. So if the N was 2, then what would the light be doing? The yellow light would be moving at half the speed of light normally. Because if this is a 2, it means this is half C. Yeah? So, I think for the exam, it's really the formula that they care about, but I would like you to write this down, because it actually is important to know that the standard is yellow light, that they shine a yellow light through the material. N is between 1 and infinity.
What's that? Refractive index.
The refractive index N of a material is a measure of how fast yellow light can travel through the material. Mathematically, N equals C over V. Oh. Are you a superhero, Siva? You have super hearing and super sight. Are you some kind of superhero? It's like at night you put on a costume or something. I'll have to think of your name now. Super Siva is a bit too simple. We need something else.
Siva hero.
Nah. It needs to be something catchier. Sebanator, maybe. Something like this. Okay. You got that? Yep. So I think maybe the next thing I probably have is a table. Values. Oh yeah, interestingly, if n could equal infinity, then you've actually stopped the light from moving, which isn't really possible. And v equals c only in a vacuum, which is what you said. So, I guess I don't give you some values yet. So, if you know the refractive index of a material, then you can use something called Snell's law. And maybe you've heard of this before. Snell's law lets you calculate the change in the angles as the light moves from one material to another material. Useful. One way of writing Snell's law is like this. Now, before you write it down, I just want to draw what the everything represents. Actually, maybe I will just draw it. So this is what happens. You have one material. So this material has refractive index, we'll call it N1. And this one has refractive index of N2. Okay? And then let's say you have some light and it comes in here. So there's our light. It hits this material and it changes its angle. Now we need a way to measure the angle. So you actually might think, oh, we should measure the angle here with the boundary. But actually you measure the angle here with what's called the normal line. This perpendicular line. Okay? We'll call this angle theta 1. And it'll come out here at a different angle. And we'll call this angle theta 2. And Snell figured out a relationship between the angles and the refractive index. So he said that sine theta 1 over sine theta 2 equals n2, not n1, n2 over n1. It's opposite the index here. That's called Snell's law. Now just before you write that down, sometimes this angle is called angle I for incident, and sometimes this is called angle R for refracted angle. In the formula book though, it's theta 1 and theta 2 for first angle, second angle. Okay? So you don't need to write this box down. If you prefer, you can just copy this down. This is, I'll write on the top, this is Snell's, 2 L's in Snell, isn't it? Yeah. Snell's law, right? Snell's law. You can all see that okay? Yeah? Okay, great. Okay. You have all of this? Yes? Yeah, okay. Have you seen Snell's law before? Have you? Okay, continue?
Yeah.
Right. I actually drew a picture here, but my one's a little bit clearer. Okay. Under certain situations, it's possible to pick an angle for theta 1 so that theta 2 is 90. And this is called the critical angle. Now, let me draw that situation for you. So, here's the boundary. Here's the normal. The light comes in at some angle C, and then it refracts at 90, which means it moves along the edge here. And if you made the angle bigger than C, it would actually reflect back in. And this is called the critical angle. It's like the angle that would make the light just about not enter the second medium. Now, let's try and think about using Snell's law here to calculate it. So we need to figure it out. Sine C over sine 90, because we know the other one's 90, that's equal to n2 over n1. Oh, what's sine 90? It's 1. So you can have this formula is that C equals sine inverse n2 over n1. But that formula doesn't always work. There's something about n2 and n1, a relationship. What's the relationship between n2 and n1 so that this formula actually works? Not equal? I mean, they could be equal, but we need something else. I suppose my question is this. Will this formula always work? No. There's a situation where the formula breaks. Can you see when? Well, let's assume we know both of them. Zero's okay, because you can have sine inverse 0. You can have sine inverse a negative. Okay, you don't know, that's fine. You can't calculate sine inverse of a number that's bigger than 1. Like, try it on your calculator. Type in sine inverse 1.1. What happens?
Error.
Error. Yep. So we need, this formula only works as long as n2 is smaller than n1. That makes this less than 1. So that's actually an important condition here. So that's the formula. A little bit of vocabulary. This is called the critical angle. And if you go beyond the critical angle, it comes back in. And that's called total internal refraction. If you're past the critical angle, then it comes back to you. Total internal refraction. Now there's actually where's this internal refraction important?
Claims.
Maybe. Nah, doesn't matter. Doesn't matter.
Fiber.
I was thinking the fiber optics, but this whole lesson is important for fiber optics because fiber optics works by sending light through the little glass prisms inside the cable. Okay, so you should write this down, critical angle. Oh, the Revita biscuits are back on sale. €2. I got my chocolate ones. Did you buy any? Good. Okie dokie. Got that? Yep. Now notice in the last lesson you did not see white light. Remember when we did the visible light? You had red, orange, yellow, green, blue, indigo, violet. Oh, thank you. That's because there's no frequency for white light. We have frequency for red, orange, green, etc., but not for white. And that's because white light is a mixture of all the colours. That is, if you have red light and you mix it with orange and green and yellow and all of them, you mix all the colours of light together and shine them together, that makes white. So there's no, you don't need to write that down. The idea is if you have all the colours and you shine them together, you make white. And by white light, I mean like, you know, visible light, the light that you see from a light bulb or from the sun. There's no colour in this light. It's not like you all look red or something, you know. So we call it white light. This one's white, that one's blue. In the middle, black. Yeah. Okay? Yeah? Anyways, that's important for something that's coming up in a moment. So another way to state Snell's law, is that? No, not quite yet. All right. I'll back onto the white light. So maybe you can tell me what's wrong with this, or not what's wrong, but what's the idea here? No, I'll do it in black. Okay. Here comes our white light, which you probably can't see. It's white. I'll put it in black. Here comes our white light. Okay, and it will change angle here. But if you look at the picture, the red goes this way, and then comes out, and then the green comes out at a different angle as well. So you need to imagine it's like there's red and green together, because they're mixed together to make white. They refract. So sine theta 1 over sine theta 2 equals n2 over n1. So sine theta 2 equals n1 over n2 sine theta 1. Okay. Let's look at the red light and the green light. Would you say the theta 1 is the same? Yeah, because they're both moving together. So they both hit the prism at the same angle, theta 1. So that's the same. And they're both in air. So we think that's the same. And they're both in glass here. So we think that's the same. So then why is this different? Why is the theta 2? Why do we have different angles here? So it must be that something in the formula here is not the same for red light and green light. Could it be the theta 1? Not really. Like, how could it be? They're both moving at the same angle. Could it be the n1? Well, not really, because they're moving in a vacuum here. This is air. So n1 is 1. So it must be the n2. And if you remember my definition, what did I say the definition was? The n for the material is only for what colour of light? Yellow. So actually the n2 is different for each colour of light. So if I tell you the n2 for glass, I'm only telling you for one colour of light. That's all. So the reason they split is because of different n2s. Alright? So you have your white light, it comes in and it splits because the n is different for each colour, and this makes different angles, and it splits the white back into all the original colours. And that's it. So why should the theta 2 be different? Well, it's because the n changes for different colours. Why is the n different? The n depends on the frequency slightly. So different colours of light have different frequencies, and this actually changes the n. It's only a slight difference, but it's enough to make the angles different here. N2 is a function of frequency. Okay. Let's see. So the next thing we need is the different ways you can state Snell's law. So I gave you one way, which is with the angles, but you can actually give you Snell's law using the speeds, the V1 and the V2. And it's actually easy to prove this. Sine theta 1 over sine theta 2 equals N2 over N1. But what's the formula for N? C over, that would be V2, and this would be C over V1. What cancels here? C is, so you end up with V1 over V2. So another way to state it, oh, and that's the third way, the V is, so let me look at the middle one here, the wavelengths, okay? So sine theta 1 over, you don't need to write this proof down, I just need you to write the results in a minute. Sine theta 1 over sine theta 2 equals N2 over N1, which equals C over V2, C over V1. But we have a formula for V. What's the formula for V? Do you remember? It's lambda F, isn't it? V equals lambda, this would be F2, and this one here, C over lambda F1. The C's cancel. Oh, sorry, lambda 1, lambda 2. The C's cancel. The F's cancel. Oh, sorry, thank you. Lambda 2 and lambda 1. The F's cancel. So you're left with, that's not clear now, I better write that in a bit clearer. 2 and 1. So you're left with lambda 1 over lambda 2, which I think is what I have here. Yeah. Now, why do the F's cancel? So there's a little fact here I didn't tell you that comes up in the last one. When light moves from one material through another, the frequency doesn't change. Now the reason for that is actually because there's a relationship between the energy and the frequency. And it's kind of a conservation of energy. When the light passes through the material, it doesn't lose any of its energy. Because remember we said in semester 1 that light is a form of energy. Remember when we did the energy types, you have like chemical, potential, magnetic. Light was one of the forms of energy. And its energy is related to its frequency. And again, we saw that in the last lesson, that the X-rays have a big frequency and a lot of energy. Okay. The F1 equals F2 is actually like a conservation of energy. Okay, so that's why I can cancel the F's and I'm left with this formula. So these, whoa! Sorry. That an angle and slowly moving, which makes it exciting. So. Close enough. These are the three ways to state Snell's law, depending on the situation. You know, sometimes in the question they give you wavelengths and they want to know, angles or whatever. So I think I should write the three down. The bad news is the only one that's in the formula book is the first one. So you have a choice. You can either just remember these or remember the proof. And these aren't that difficult. In fact, these are easier because the 1, 2, 1, 2 is the same order. 1, 2, 1, 2. It's only the first one that actually is the opposite. Okay, so you can write those three down. Got that? You got those three? Yeah? Can we go on? So, the next thing we have, one use of Snell's law is in a lens. When light enters a glass lens, it will refract. But the lens is curved. This will result in different angles. And the lens is made carefully so that it refracts to converge. So I'll explain this with a diagram, how the lens works. So here's the lens. And here's the light. So the light comes in, it hits the lens. The angle, remember, right, let me draw this a little bit. Comes in straight. Okay. What's the angle? Well, what we do is we draw a tangent here. This is a tangent. And then we draw a normal here. This is a normal. And this is the angle here. And it refracts off at a different angle here. Let's imagine another piece of light comes in, say, here. So once again, we draw our tangent, we draw a normal. Here's the angle. And it refracts again. The way they make the lens is so that the θ2 is the right angle at each location, so that the light always refracts and meets up at a single point here. Like, this curve is carefully designed so that the θ2 is the right angle to make sure that it hits a point here. So up the top here, well, that's really all there is to say about it. This curve is very carefully calculated so that you can get this effect here, that all the light is refracted so that it hits one point. Okay, that's how a lens works. So the only thing I really need you to write here is that this is an application of Snell's law. One use of Snell's law is when light enters a glass lens, it will refract, but the lens is curved. And then you could just say the lens is carefully made so that the refraction will cause the light to converge. So it's carefully designed. So there's oh, nice. No chocolate ones. She ate all your chocolate ones. They're the nicest ones. I would have 2 packs a day. I have one in the morning and one in the evening as a snack. So delicious. Okay, you got this? Now, it's important for me to say, just to be clear, the colour of light depends on the frequency. Depends on the frequency. Okay? So if you could change the frequency, you'll change the colour. But if you change the wavelength, you don't change the colour of the light. So I just need to clear this up, because I was actually last year, it's like a bit confusing. It's because, you know, you can say, oh, it depends on the frequency or it depends on the wavelength. That makes the colour. And that's kind of true if you're in a vacuum. But then the problem is, when you have a material like glass, remember we said the frequency doesn't change. Neither does the colour change. But the wavelength does change because it slows down. So something must change. So what precisely makes the colour of the light is its frequency, not its wavelength, to be precise. Yeah? It's okay, Matt? Yeah? So I don't know what you were told in school before, because like you could have been told both, but if we're being technical, it's the frequency that determines the colour of the light, not its wavelength. Okay? Actually, you know what? That's important enough for you to write down. Just say the frequency determines the colour of the light, not the wavelength. Yeah. Yeah. Okay. Continue? Yep. Right. Okay. Let's have a look. Let's do this question together. Just the one example. The speed of red light in glass is 2 times 10 to the 8. What is the refractive index? Okay, so what formula do I use for the first part here? Yeah, you can check if you need to. The refractive index, how do I calculate it? N equals C over V. Okay, so for part A, N equals C over V. What's the C? 3 times 10 to the 8. And what's the speed of the red light in glass? 2 times 10 to the 8. So what's the N here? It's 1.5. Okay? Yep. All good with that so far? Right. The refractive index of air is about 1. So N1 is about 1. Red light enters some glass from the air at an angle of 20. What angle does it travel at when it enters the block of glass? So I'll draw the picture for you. So here you go. Here's the glass. And here's the air. And that's the normal. And the red light comes in at an angle of 20. And I want to know what's the angle afterwards. So let's do this together. Sine theta 1. What's theta 1? 20. Over sine theta 2. Yeah? That's equal to N2. What's N2 here? Oh, I think I tell you in the question. For glass, for this block of glass, it's 1.33. Why did I make it different to this? I don't know. Doesn't matter. It's 1.33 for this block of glass. And N1, what's N1? 1, yeah. Okay, I'll let you calculate theta 2 for me. It's a simple maths problem. You see okay, Tim? Yeah. $14.9. Is that okay? Is that okay, guys? Can I continue? Yeah. Now some light is shone from the glass to the air. At what angle should the light be shone at so that the light refracts back into the glass? In other words, what is the critical angle? So for part C, what's happening is this. You have your glass, and you have some light that's shining through the glass, and it hits the edge of the glass, and you don't want it to go into the air. Instead, you want it to come back in. Yeah? That's called the critical angle. Now, you have a formula for the critical angle. It's sine inverse. What's the formula?
N2 over N1.
N2 over N1. Now, what is the N2 here? No, actually. See, we have to be careful. Because now this time, this is the N1 and this is the N2. So the N2 is actually 1. And the N1, 1.33. Okay. .8 degrees. Oh, by the way, one of your 4 experiments you'll do is calculating the N for water. I have a very nice little piece of equipment for you to do that. A little glass tank full of water, and you can set the laser and you can measure the angles. So that 1.33 is something you'll calculate in one of your experiments for
This is
water.
lab report.
Yeah, one of the lab. Yeah. You do 4 experiments. You only need to write up one of them, type up one of them. Okay, you got this one? Yeah. Question marks? No? Everything's okay with this? So really there's a couple of new formulas. So you can appreciate that the first and second lesson is not so big on the exam. This is more now exam stuff because you have things to calculate. Okay? So we have exactly 10 minutes left. So if you just spend the last 10 minutes getting a start on your homework, okay? These ones now are starting to get harder. Let's see how many I gave you. Yeah. Number 4 is hard, but the bad news is it was on the exam twice. Now what's really funny about number 4 is it's really, really hard, and I did it in class, and I was shocked when a student chose to do number 4. It was a section B question, because I would have thought they would have remembered how difficult it was to do in class, okay? So I do need you to do number 4 because it is on the exam. It'll probably be a section B question. It's come up twice. If it comes up, don't do it. But it's good that you try it, okay? And yeah, number 5 was also an exam question, I think, as well. But just 10 minutes, please.